Welcome to another instructional video from OWL, the wise choice in fiber optic test equipment. I'm Professor Jim Powers. This video will demonstrate how to certify a single-mode fiber optic link using a WaveTester optical power meter and a Laser Owl series single-mode light source. There are 5 main steps in the process of certifying any fiber optic link. These steps are gathering link information and accessories, checking equipment and accessories for proper operation, entering link information into the certification tester if available, and setting an optical reference, also called zeroing, taking insertion loss measurements and storing test results, and then downloading stored test results to a PC and printing a certification test report. Before beginning any fiber test, the user must gather the necessary link information and accessories required to complete the test. Link information is used to help determine how much loss is acceptable for the fiber under test, otherwise known as a link budget. Optical loss measurements are compared to the link budget to determine if the fiber is good or not, which is the same as saying pass or fail. There are 5 key parameters that apply to any fiber optic test. First is the fiber type, which will be either single mode or multimode. In the case of multimode, this could be either 62.5 or 50 micron. Next is fiber length. It is important to know how much fiber is in the link under test in order to determine how much loss is acceptable for that particular length of fiber. Some OWL testers can be used to measure the end-to-end length of the fiber automatically, including the FiberOwl4 Bolt optical power meter. Otherwise, the user can use jacket markings, installation documents, or other length measurement methods such as OTDR. For best results, avoid estimating the fiber length whenever possible. Third is number of connections. A connection is the point where 2 fiber connectors mate together, such as in a patch panel, wall plate, or mating sleeve. Fourth is the number of splices, which can be either fusion or mechanical. For the purpose of calculating a link budget, most cabling standards do not distinguish between fusion and mechanical splices. Lastly, the user must determine what wavelengths they will test at. For multimode, this is 850 and or 1300 nanometers, and for single mode, this is 1310 and or 1550 nanometers. When using a micro-owl or fiber-owl optical power meter, these parameters can be entered directly into the device to calculate the link budget. However, if the link budget needs to be calculated manually, this is done simply by adding together the fiber loss, connection loss, and splice loss. Fiber loss is given in dB per kilometer and varies based on the fiber type and wavelength. To calculate fiber loss, multiply the fiber length in kilometers by the fiber loss. Connection loss is the number of connections multiplied by the dB loss per connection. Splice loss is the number of splices multiplied by the dB loss per splice. Most users will follow the fiber, connection, and splice loss specified in cabling standards, such as the TIA-568. It is also helpful to determine the connector type used in the link under test, which will help determine the right reference cable configuration to use. For accessories, it is highly recommended to keep at least 3 patch cables on hand, since there are 3 reference methods: 1 jumper, 2 jumper, and 3 jumper. Mating sleeves may also be required for some link configurations. Refer to OWL's video on reference methods for more information. Finally, if testing multimode fiber, the launch cable attached to the light source will also need to be wrapped around a mandrel according to cabling standards specifications. Refer to OWL's video on mandrels for more information. As you can see, we've gathered all the equipment and accessories we will need for this test. In this case, we're using the WaveTester optical power meter and Laser Owl single mode light source. You can also see that we've got 3 patch cables here. Now, why do we have 3 patch cables? Well, what I'm demonstrating here today is how to do a dual wavelength measurement, so testing at both 1310 and 1550. Because there are 2 ports here, one for each wavelength, we will need a reference cable for each port. The 3rd patch cable will stay with the WaveTester on its side of the test. So, in order to check these patch cables, we simply press the power button on both units. And on the light source, you'll see that we have 1310 nanometer lit by default. So this is the wavelength we're going to initially use to check our patch cables. Now on the WaveTester, as you can see, we have the 850 nanometer wavelength set here. We will need to change this to 1310 nanometers. Now a nice feature of the WaveTester is that when you power it off, it will remember what wavelength you were on. So when you power the unit back on, it will come back to 1310 in this case. You can also see that the display says low. Now the word low simply means that there's no measurable amount of light coming into the photodetector. As you can see, we have the dust cap on the detector port. So when we take this off, you'll see that we actually get a reading. In this case, we're reading room light, but we will actually get a real power reading when we connect in our patch cables when we're testing them. So I'm going to do that now. First cable we want to check is the cable we'll be using for the power meter side of the test. So we plug it into both ports. And our target value is minus 10.0. Now as you can see, we have a value of minus 10.0 here. This is pretty close to minus 10. Now the actual value is going to be higher or lower, but it should be fairly close to minus 10. What we want to make sure is that we are not exceeding minus 11 dBm. If we're exceeding minus 11 and cleaning off the connector end faces does not work, then we will need to consider replacing that patch cable. But for now, this patch cable is okay to use. So what we're going to do is we're going to replace the dust caps and set this patch cable aside for later. Next, we take the second patch cable and we plug it into the testers like we did before. Now, as you can see, we have a value of minus 10.3, 10.2, somewhere in that range. Now, this is an okay reference level. We're still, still not reaching minus 11 dBm. So this value right here is okay to use. So now that we've checked this patch cable, it's perfectly acceptable to zero out the equipment with this cable attached. So to do that, we simply press and hold the unit's 0 button here, and it zeroes out the power meter. And as you can see, we have a dB reading now. Okay, so our reference level is hovering around 0 dBm, or I'm sorry, 0 dB. dB is what you use to measure loss. So we've got 1310 nanometer wavelength zeroed out. So let's just take the patch cable out of the power meter, but we'll leave the patch cable attached to 1310. We will connect our last patch cable to the 1550 port to check that patch cable and to zero it out at 1550. Okay, now as you can see, it says low still. That means there's no light coming in. Reason being is that we have not switched our light source wavelength over. So we press the lambda button on both units. So as you can see, 1550. We also want to make sure that our power meter is set to 1550. See, it says 1310 here. We have to press the lambda button so that it reads 1550. Now, in order to check to see if the patch cable is good or not, we have to be in dBm mode. So we have to change this back to dBm units by pressing the units button. Okay, and as you can see, it says minus 10.3 roughly. This patch cable is also okay to use for our test. So to zero out this equipment, we simply press and hold the unit 0 button to zero it out. And as you can see, we have a reference level of around 0 dB. What this means is that our equipment has been zeroed. We've checked our patch cables. The patch cables are okay to use for our test. So once we've done that, we simply disconnect the patch cable from the power meter. And now we are ready to take measurements. Once we've zeroed out our equipment and accessories, we can take our testers and connect them into the link that we want to test. Now, what we'll need to do is we'll need to take the light source with its reference cables to one side of the test, and then we take the power meter with its patch cable that we set aside earlier. We take that to the other side of the test. Now, what I've done is I have this this box here, it simulates a fiber link. So in this case, it's simulating a 6-strand cable. There's a patch panel on side B and a patch panel on side A with 6 ports in it. The goal of this test is to test all of these fibers at both 1310 and 1550 nanometers. So what the first thing we need to do is put our patch cable back into our power meter here. Okay, and then just to keep things consistent and organized, what we want to do is we'll just test at 1310 nanometers first. To do this, simply press the lambda button so that both units are set to 1310. And then we plug into port number 1 on both sides. Now make sure you use the 1310 nanometer reference cable here. All right. Now, as you can see on the power meter, we have a dB reading. It says around roughly minus 1.1 dB. Okay, this is how much loss we are reading across this link here. Now, if you look here, there's a negative sign. What this negative sign means is that you are measuring loss of your link. So the light is losing strength as it goes from the light source through to the power meter. Okay, this is what we want to see. We want to make sure that we actually see a negative sign here. If we do not see a negative sign, that means there might be some procedural issue, and that we'll have to address at a later time. So make sure that there's a minus sign here, and once we've taken our reading, all we have to do is simply press the save button here to save the reading at 1310 nanometers. Okay, as you can see, now there's a little floppy disk icon here. That means that there is data stored in the meter now. And if you noticed that there was a fiber number here, 001. This is actually test reading number 1 that we're taking. So the next thing we need to do is to measure all of the ports here. Now, one helpful tip that I'd like to cover before I continue is that the best way of taking dual wavelength measurements with this particular test kit is to store all the readings at one wavelength first, then store the 6 readings at the other wavelength after that. Reason being is that you don't have to keep pressing a wavelength button, switch back and forth from port to port. Simply test all the wavelengths, or test all the ports at one wavelength. Then you only have to change the wavelength once on both units. So what I'm going to do is I'm going to speed up the process here and store all 6 readings. And finally, we store a reading for fiber number 6. As you can see, if you noticed that the fiber number kept incrementing from 1 to 2 all the way up to through 6. Now, what we're going to do is we're going to switch the wavelength on both units. So we just simply press the lambda button to do that. We're switching to 1550 nanometers. Okay, again, see, remember that low means no lights coming in because we are not using the 1550 reference cable. Once we connect in, we will get a reading. So what we want to do is we'll take the 1550 reference cable, plug back into port number 1, and then again the power meter cable plug into port number 1 as well. Okay, as you can see, we get a power reading. So when I hit the store button, you'll see what happens here. Notice it says number 7. Now this doesn't mean that you're storing port number 7. It just means that this is the 7th reading that has been stored in the WaveTester. This is not a concern. When the WaveTester downloads its data, it organizes the test readings. It basically puts the first 1310 reading it took with the first 1550 reading it took. That's why it's very important to make sure that you test the fibers in the same order at both wavelengths. So as you can see, we've taken a reading here at for port number 1. I'm just going to speed up the process again here and test all readings at 1550. And finally save a reading for fiber number 6 again, but at 1550 this time. Now as you can see, we had the number 12 show up there. So we stored 12 readings, 6 at 1310 and 6 at 1550. So once we've taken all our readings, now we can take the WaveTester to a PC and download them into a certification report. Once data has been stored in the optical power meter, test results can be downloaded to a PC to produce a certification test report. First, install the USB driver and OWL Reporter software from the supplied CD or a USB flash drive. Connect the power meter to the PC using the supplied USB cable. And then power on the power meter. Then start the OWL Reporter program. The program shortcut can be found in the Start menu. When the software has started, the screen will initially say no data loaded as shown here. Download the test results to the PC by pressing either the download menu option or the download button. While downloading, the status bar will say searching for OWL device. Specific to the WaveTester, once test results have downloaded to the PC, OWL Reporter launches a link wizard. Users will be prompted to enter link information into dialog boxes, starting with the cabling standard. Click the arrow in the drop-down menu to show a list of cabling standards, then click on the standard to select. Once the chosen standard is selected, click Next to continue. Click the drop-down arrow to show a list of fiber types, then click on the appropriate fiber type. Then click Next to continue. Enter the fiber length by selecting the appropriate measurement units, then typing the length number. Click Next to continue. Enter the number of interconnections and splices for the fiber under test. A connection is simply a patch panel, wall plate, or other mating sleeve. Likewise, count the number of total splices in the link under test. Most cabling standards do not distinguish between fusion and mechanical splices. Click the New Organization button, then enter the organization name and telephone number. Once the organization name appears in the drop-down box, click Next to continue. Enter the date of test. By default, the current date is displayed. However, if the date of test is different, use the drop-down menu to change the date. Finally, enter a descriptive name for the link under test. Once the test results have successfully been downloaded, the data will appear in the OWL Reporter screen. The test results can be viewed in 2 different formats. This view is called Circuit Detail View. It shows detailed information about a single fiber run. The other view is called Circuit Summary View. Circuit Summary View shows basic information about a group of related fiber runs. Certain buttons become active when Summary View is selected. Pass-Fail, Overhead, which shows how close the test is to its fail point, or Optical Loss. Toggle between Summary and Detail View by pressing this arrow button. Test results can be printed from the File menu or Printer button. The printout will show test results based on the currently selected view. The reports are formatted to look like the OWL Reporter screen. This has been another instructional video from OWL, the wise choice in fiber optic test equipment. For more information about additional instructional videos, or OWL fiber optic test equipment in general, please visit OWL's website at owl-inc.com. I'm Professor Jim Powers. Thanks for watching.